Today's theme is the end of Dijkstra's algorithm, one of the most significant results in theoretical computer science research in 2025. To start off, I'd like to introduce you to someone. And that's myself, a student who has to deal with immense amounts of workload. 5 supervisions this week, group project due tomorrow, society work, and that's right, this technical talk. Cambridge life can really feel like an endless marathon. And so to try my best to meet all my deadlines, I often catch myself asking, what is the single most urgent task right now? But priorities can change, and keeping a perfect ordering between tasks is really, really tiring. And so I start to seek an alternative. Let's start by picking a meaningful boundary. Let's say I want to find out what needs to be done before this Sunday. I complete that batch of workload, then I move the boundary forward. Although sometimes I'd start with saying, I'll finish everything before Sunday, and realize halfway through that this batch of workload is too much to handle. Rather than forcing myself to do all of it, I find it better to shrink the boundary. I fully complete a smaller batch I can guarantee, take a short break, then repeat the process to complete the rest. Now, you may be wondering, what does all this have to do with today's talk? I promise you that it will come together towards the end. Today we want to solve the single source shortest path problem. We're given a graph like the one you see on the left, a starting vertex S, and we want to know the shortest distance from S to every other vertex. On the right here is Dijkstra, the famous computer scientist who formulated an algorithm that solves this problem around 60 years ago. Let's quickly refresh what his algorithm is. We have a heap on the right, which maintains a sorted order of the estimated distances of vertices which we have not visited yet. And initially, that's every vertex. At each step, we extract a vertex with minimum estimated distance from the heap. Then we perform a relaxation step for all edges originating from this vertex. In this case, we update the estimated distance of vertices A and B to 2 and 4. Now, we look at the heap and find a vertex with minimum distance again. In this case, it is vertex A with distance 2. And so we extract A from the heap and update the distance estimates for vertices B and C. And after the update, vertex B now has the minimum distance among those in the heap. So we extract it from the heap and process it. I think it's probably clear what the gist of the algorithm is by now. We've processed vertex C next, followed by vertex D. Now, the final distances are settled and our algorithm terminates. That is Dijkstra's algorithm. It runs in n log n plus m time, where n and m are the number of vertices and edges respectively. Well, that's pretty good, right? But there's always some researchers who are just not satisfied. The natural question that they ask next is, can we do better? Can we be more efficient than n log n plus m? And really, many researchers have made efforts over the past 60 years or so to try to beat Dijkstra's algorithm in one way or another. But simultaneously, 5 researchers have successfully proven in this paper, published 3 years ago, that Dijkstra's algorithm is, in fact, universally optimal. Well, okay, now you may start wondering, wait a second, what's the point of today's talk if Dijkstra is supposed to be universally optimal? Well, let's take a closer look at the abstract, should we? If you look at the right here, they say that we prove with Dijkstra's algorithm, with an efficient heap guarantees universal optimality for the problem of ordering vertices by their distance from the source vertex, which we call the distance order problem. So they're talking about this distance order problem, which seems to be slightly different from what we usually call the single source shortest path problem. Let's have a more detailed look. So given a graph with a source, the distance order problem requires us to output both the shortest distance from the source to every other vertex and an ordering of vertices, say v1, v2, v3, up to vn, such that the distance to v1 is at most the distance to v2, the distance to v2 is at most the distance to v3, and so on. Now, intuitively, this ordering problem is at least as difficult as sorting, which we know takes n log n time. Combining this with the time to finish reading the input, we see that the distance order problem takes at least n log n plus m time to solve, which is why Dijkstra's algorithm is optimal. In fact, when we were doing an example of Dijkstra earlier, we kept track of a heap, S, which maintains a sorted order of these unvisited vertices by their distance estimates. And this sorting barrier is precisely the bottleneck of Dijkstra's algorithm. However, if we have an algorithm that avoids maintaining a global sorted order of vertices, that gives us the chance to break the sorting barrier, hence beating Dijkstra in terms of time complexity. Well, in July 2025, 5 Chinese researchers, Duan, Mao, Mao, Xu, and Yin, published a paper breaking the sorting barrier for directed SSSP. And if you take a look at the abstract, it seems that they found the first result to break the m plus n log n time bound of Dijkstra's algorithm on sparse graphs, showing that Dijkstra's algorithm is not optimal for SSSP after all. Now, when this paper came out, a fair portion of people have suspected the legitimacy of this result. What is this algorithm really doing? Well, we'll find out right now. In today's talk, we'll first look at the various building blocks that make up the main algorithm, then we'll have a glance at the main result itself, and then we'll compare the author's work with some other existing results for SSSP, and finally, we'll discuss some wider implications of this result. So firstly, the building blocks. Here's some notation that we'll use today. The first one here, which I'll call d hat v, denotes the current estimate of the shortest S to V distance. And the second one, which is d of v, denotes the true shortest S to V distance. You should be familiar with this from algorithms too. And if the two values are equal, then we call such a vertex complete. Otherwise, it is incomplete. That's very simple. Okay, so the first building block here is the bounded multi-source shortest path problem, BMSSP. Given a set of sources, S, with initial distances d hat x for all x in S, and an upper bound b, for every incomplete vertex y, we suppose that the shortest path from the source to y passes through some vertex in S. And the task here is to determine whether d of y is smaller than b or not. If so, we should also find the exact value of d of y, but if it's not, we don't really care. I think it's quite good to think about this problem using an input-process-output model, and we know that the input to this problem is an upper bound b and a frontier or source set S. Now, where does this S come from? Actually, you can think of it as our version of the heap in Dijkstra's algorithm. They share kind of similar roles, but the data structure they use themselves is slightly different. Meanwhile, the output of this algorithm would be a set of newly completed vertices, U, under an exploration bounded by the upper bound B, as we see above. Okay, let's look at an example where the set of sources here is vertices S, A, C, and F, basically the dark-colored vertices here, and say we have B equals to 6. At a high level, we want to determine the exact shortest path values for all the vertices that are on the left of this boundary. But for vertex G, for example, it is on the right of the boundary, and we don't really care about its exact distance. We only need to know it's greater than or equal to 6. Now, maybe this formulation of the shortest path problem does seem slightly odd to you. And it's not really clear why we're considering this formulation. But it turns out there is a self-contained divide-and-conquer strategy to solve the SSSP problem, in which each recursive subproblem is an instance of the BMSSP problem. That means BMSSP is a reusable subproblem that the main algorithm calls many, many times. Let's give a name for this recursive subproblem. Let BMSSP L, B, and S denote an instance of BMSSP with recursion level L, source set S, and upper bound B. It should return a set U of vertices that this call completes. Okay, so let's consider the so-called recursion tree of this main algorithm. At the top level, the instance with parameters little l, positive infinity, and a singleton set containing only the source is basically equivalent to SSSP if we think about it. And by design, we set little l to be equal to log n to the power 1/3, and this will be helpful for the runtime analysis. Okay, so how might we want to split one problem into recursive subproblems, since we're doing some sort of divide and conquer here? Let's consider an arbitrary instance, BMSSP with parameters L, B, and S. Suppose there is an oracle that gives us some B1, such that half of the vertices have a true distance smaller than B1. So that's convenient, right? Because it divides our problem into two halves. We first only have to solve the vertices with distance smaller than B1, as you can see, the left child, and then we can solve vertices with distance between B1 and B, as you can see in the right child. So the first recursive call has parameters L minus 1, B1, and S1, and this first call has returned a complete set U1. Once we have this set, we relax all the edges originating from a vertex in U1, and then we can use that to help us to solve the second subproblem, which then returns a return set U2. So this will all be clearer with an example. Let's look at this graph where we have the parameters B1 equals to 5 and B equals to 9. And the set of sources is A, B, C, and D. So in the first half, we have S1 equals to A, B, and C, since their estimated distances are smaller than 5 and they're in the source set initially. Okay? The second half is a little bit more involved. In between the first and second half, we relax all the edges from A, B, or C, which are the gold edges, if you can see on the screen. The source set S2 is then computed in a rather special way. Of course, we want to include vertex D because it was in the original source set, S, and it also has distance estimate between 5 and 9. However, we also need to include vertices E and F because after we perform the relaxation step, the distance estimates of E and F are now 7 and 8, which are between 5 and 9, so we want to include them in S2. So as a result, S2 would be equal to D, E, and F, and we complete all of them in the second recursive call. So that's the high-level idea of the strategy. But in the actual algorithm, life is never that simple, and we divide into 2 to the power t subproblems instead of just 2 subproblems. And t here is log n to the power of 2/3 for the same reason of making sense of the final complexity. But the main idea is the same. We solve subproblem I, use its return set ui to relax edges, compute the set si plus 1, and so on. But now you may have a question. How exactly are we going to partition the current problem into these 2 to the power t subproblems efficiently? Well, it is perhaps no surprise that we need some help of data structures, which brings me to the partial sorting heap, our next building block. This is a sort of new data structure that supports partial sorting. We kind of want to maintain the general order between values, but not so strictly. More formally speaking, we're given at most n key value pairs to be inserted, an integer parameter m, and an upper bound b on all values that are involved. And we have a data structure here that supports the operations insert, batch prepend, and batch extract. We'll see very shortly what they mean. Now, this is a block-based data structure, where m, the parameter there, it denotes the maximum block size. So in this picture, for example, m could be equal to 3 or anything above 3, really, since all the blocks are of size at most 3. In general, the partial sorting of the data structure comes when you look at the values within each block and between different blocks. So within each block, we allow the values to be unordered. But then between blocks, we must have a total order between these values to exist. Okay, so let's take a look at the specific operations. Insert is quite intuitive. We locate the exact block where the given pair's value lies, and we just insert it at the block that we want. So for example, the value 15 should lie in the second block, as you can see. And for batch prepend, we insert L key value pairs, where L is just some parameter. But the catch here is that each value inserted is smaller than any value currently in the data structure. So here, for example, I made this particularly simple example where we just have to insert a single block of 3 elements in front of the entire data structure. Okay, so how about the batch extract operation? Well, this operation is used for retrieving the smallest up to m values present in the data structure, where m is the parameter we used for the block size previously. And it is really not that difficult. If we look at whatever is in the frontmost block, we basically have what we want to extract from the heap. And the upper bound, we need to return a boundary that lies above extracted values and below the minimum remaining value. So in terms of how to calculate this boundary, we can just basically compute some number that is just slightly bigger than the maximum value we remove. For example, here, 20 is just slightly bigger than the maximum value, which is 19, and it's below the minimum value that remains in D. Okay? So now we have this efficient partial sorting heap. But then, well, that's good, but however good a heap is, if combined with order n operations, it's not going to help us to beat Dijkstra here. Let's look at this graph here. How would our divide and conquer strategy that we mentioned earlier work on it? Well, let's start by initializing the frontier of S1, which is the frontier for the first subproblem, to only contain the vertex S, so the source vertex here. Let's recurse on the first subproblem then. And let's say the first subproblem allows us to solve for all vertices with true distance equal to 0. We obtain the completion set U1, which consists of these 5 vertices on the left. Well, and then we relax the out edges of U1, which makes us relax the distances for W1, W2, W3, and W4. And now we add all of these vertices into the next frontier, S2. Well, what we see here is that this makes half of the graph's vertices in S2, and in general, the frontier of some call of BMSSP can reach O of n, and we don't really want to maintain that many vertices in the heap. Just think of the problem we had with Dijkstra, where we had to insert n vertices into a minimum heap, and that kind of just breaks the time complexity, and we don't want to do something similar here. Fortunately, we do have a solution to this, and that is to find a set of pivots from the frontier, and only do the heap operations on those pivot vertices. Well, how does finding pivots work exactly, though? We will again illustrate the main idea using an example. Let's say we're working on the frontier, which consists of 4 vertices, A, B, C, and D, and we want to find a subset of it as pivots. Now, imagine we fix a new parameter k, say here k equals 2, and then we run k rounds of relaxations, starting from the frontier S. Let's call the set of vertices discovered by this process as W. So W is just whatever is enclosed in this bounded region. Now, we can show that there is an algorithm for all k that runs in O of k times the size of W, that returns a subset of S as our pivots P, and the extra requirement is that the size of P is at most 1 over k times the size of W. And that algorithm is surprisingly simple. Consider the edges that contribute to shortest paths from the source. We can show that using those edges, we can form a so-called shortest path tree. And if we're only looking at these vertices in W, as you can see here, we get a shortest path forest, which is a collection of trees. And within this forest, we will take the roots of the trees that have size at least k as pivots. So that's vertices B and D here. Now, why is this set of pivots guaranteed to be small? Well, because if you think about it, we're looking at a collection of trees. And every vertex in this set W, it belongs to exactly one tree. And one tree has exactly one root. So the number of trees that have size at least k is at most 1 over k times the size of W. And if we pick those roots, we would obtain the desired set of pivots that we want. Well, what happens to the other vertices, like vertex A, C, and X here? What are we going to do about them? Well, it turns out we don't have to worry about them, right? Because we have done k rounds of relaxations at the start. And doing k rounds of relaxations from the frontier is enough for us to complete every single vertex. Okay. To sum up what we just said, we have a subroutine, find pivots B and S, that takes in the parameter B and frontier S, and returns 2 sets W and P, such that P is a subset of S, and P is at most 1 over k times the size of W. So far, what have we got? We got BMSSP, and we also got the divide and conquer strategy, We got a partial sorting heap, and then we got pivot finding for doing heap operations on fewer vertices. And now let's put all of these ideas together. So we've mentioned divide and conquer, right? More specifically, for each BMSSP call, we want to partition our problem into 2 to the power t roughly balanced subproblems, where we solve subproblem 1, then subproblem 2, and so on. And earlier subproblems are for vertices with smaller estimated distances at that time, but we do not need a total ordering of these vertices. Across subproblems, let's say we keep track of a boundary little b, which indicates we're saying that all vertices with distance smaller than little b are already complete. So what does a subproblem really do? It tries to push the boundary forward. That is, we try to make progress from little b to some new b prime, as you can see here. Well, b prime might be smaller than b here because it is possible that too much work needs to be done in the current recursive call with parameter b. And by design, we'll just adjust our boundary to a smaller b prime, which guarantees we can return a completed set that is large enough, and we'll leave the rest for other recursive calls. I guess we have one more consideration here. A couple of slides ago, we wanted to partition a set of vertices into 2 to the power t subsets, where we want a partial sorted order of vertices by their estimated distances. Well, it turns out we can use the partial sorting heap, D, exactly for this purpose. Conceptually, this heap serves a similar purpose as the heap in Dijkstra, where we store some vertex distance pairs. When we want to recurse into a new subproblem, we just have to batch extract m vertices with the smallest distances, use those vertices as the set for a recursive call, and then just repeat. We now have all that is needed to come up with the final algorithm. Put simply, it consists of 3 steps. Firstly, we prune the frontier S, obtaining a set of pivots P. Secondly, we initialize the partial sorting heap with the pivots P. And then we divide the problem into 2 to the power t subproblems by repeatedly batch extracting a set of vertices with minimum distances away from D. We solve that set of vertices, and we repeat it until the set is empty, or we have reached a good enough size of U. What do I exactly mean by that? After we solve all the subproblems, or solve enough subproblems that we want, we return a new boundary B prime and a completed set U. There are 2 cases. If B prime is equal to B, as we said earlier, this is a successful execution. Otherwise, this execution is partial, and we have made sufficient progress that we are willing to let the remaining recursive calls do the work. Okay, let's look at the time complexity of this algorithm. Let's pay attention to these 3 parameters. We have k, t, and recursion level. We will only track the 2 dominant costs. The first one is the total time for find pivots, and the second one is the total overhead from the partial sorting heap. So firstly, the total cost of find pivots across all calls belonging to the same recursion depth can be shown to be O of n times k. The exact argument is rather subtle here, but the key idea is that the sets produced by calls at the same depth are disjoint, and so each vertex only contributes to O of k work per depth. And by design, the recursion depth of this algorithm is log n to the power 1/3, which is L over here. So the total cost for find pivots is just k times n times L, which is n times log n to the power 2/3. Okay, let's look at the heap cost. For the heap cost, actually, we can show that insert dominates the runtime overhead with an amortized cost of log n to the power of 2/3 per pair inserted. However, there are only OM insertions in total. And why is that? That's because each edge only triggers an insertion when it gets relaxed. Therefore, the total overhead from the partial sorting heap D, and hence the final time complexity of BMSSP, is m times log n to the power of 2/3. And this breaks Dijkstra's sorting barrier on sparse graphs, which means graphs with m much closer to n than to n squared. So indeed, this result is legit, but this algorithm is still slower than Dijkstra on dense graphs. Now, I would like to get back to the very, very beginning of this talk, where I introduced the seemingly useless analogy about work management. Coincidentally, the first approach here, where I keep asking what the single most urgent task is, seems exactly like Dijkstra, where I keep asking where the single closest incomplete vertex is. However, we can instead pick a sensible boundary, complete a batch of work before that boundary, and then move the boundary forward. This is essentially the philosophy behind BMSSP, Instead of trying to finish everything in one go, we repeatedly make controlled progress by solving manageable subproblems, and we push the boundary forward. Now, we're going to evaluate this result and explore some of the related work on the SSSP problem. We have an algorithm that solves the problem in m times log n to the power 2/3 time, but as you may know, since Dijkstra takes n log n plus m time, this improvement is only meaningful on sparse graphs, but not in general. Well, regardless, an improvement is considered an improvement, and this is still seen as a very significant breakthrough for the SSSP problem, which won the Best Paper Award at the 2025 Symposium on Theory of Computing. I guess another question that people have in mind when a better shortest path algorithm comes up is that, are we now expected to know this algorithm in our next job interview, for example? Or will this new algorithm be applied to every existing technology? Is the improvement significant enough in practice? Well, we do have some experimental results from a team from the Federal University of Campina Grande, Brazil. And in this graph, the orange line is BMSSP, the blue line is Dijkstra, and the green line is their runtime ratio on sparse graph up to n equals to 1,000,000. I guess by the complicated nature of this algorithm, it is no surprise that it looks like Dijkstra still performs much better than BMSSP. But the interesting part is, if you look at the green line, it keeps dropping as n increases, which suggests BMSSP may eventually outperform Dijkstra on some extremely large graphs. But anyway, despite the theoretical improvement, major constant factor optimizations are still needed before BMSSP beats Dijkstra in practice. And so I'm glad to say that we have not reached the end of Dijkstra yet. In fact, the success of an algorithm is really not one-dimensional. It is far more than just its asymptotic complexity. And that is true for problems beyond SSSP, and there are like so many factors that could be taken into account. In 2023, Duan, Mao, Xu, and Yin, the same researchers from today's paper, came up with an algorithm for the SSSP problem, which runs in O of m times square root of log n log log n. Sounds decent, right? Unfortunately, this algorithm only works on undirected graphs, and it is randomized. Wait, hold up. Are we saying randomized algorithms are bad here? Not at all. Check out the Miller-Rabin primality test, which is a randomized algorithm for determining if a number is prime, and that is still one of the most simplest and fastest tests of the same kind. Well, what else? Apparently, some linear time algorithms for SSSP exist. In 1999, Forup discovered a deterministic linear time algorithm for SSSP, only in the special case for undirected graphs with positive integer weights. And that assumes multiplication takes constant time as well. So I really believe that in terms of the SSSP problem is concerned, there are still many paths for further development, and we've certainly not reached the end yet. So what are some possible next steps? We know that the BMSSP algorithm only beats Dijkstra in the case of sparse graphs. What about the general case? What about negative edge weights? What about faster algorithms that actually have a smaller constant factor? There are many research directions in shortest path algorithms, I think, and the success of the BMSSP algorithm only suggests that many further breakthroughs are possible. So we've reached the end of today's talk, but before I finish, I want to briefly reflect on what I think today's talk is really about. Of course, the BMSSP algorithm itself is probably not something most of us will implement tomorrow. For now, I think if you need shortest paths, you should probably still use Dijkstra. But in my opinion, the value of today's story goes beyond the algorithm itself. Well, I think there are three things. Firstly, the importance of seeking breakthroughs. For decades, Dijkstra's algorithm felt almost undeniable to be the standard solution for shortest paths. Yet this paper managed to challenge that assumption and push the boundary forward. In life, we often choose to satisfy rather than to aim high. But I really admire the authors of this paper who went the extra mile and actively sought breakthroughs, both in the field of algorithms and in their careers as computer scientists. I think it is an amazing mindset to aim for breakthroughs rather than simply satisficing, at least in some aspects of life. Secondly, it reminds us that success is multidimensional. In algorithms, we care about time complexity, but also input assumptions, practicality, many other factors. Similarly, success as a person is rarely captured by a single metric. Finally, the study of algorithms is genuinely fascinating. Even for problems that seem completely settled, like shortest paths, there may still be new surprises waiting for us to discover. I would like to thank John for the opportunity and my mentor Jamie for much valuable advice. Here are my list of references, and I'd like to end with the following quote: "Raise your quality standards as high as you can live with, avoid wasting your time on routine problems, and always try to work as closely as possible at the boundary of your abilities. And do this because it is the only way of discovering how that boundary should be moved forward." Edgar Dijkstra. Thank you for listening.